Namaste, my dear students. Welcome back to physics online class. In today's video, we are going to start a new topic, that is second part of the second chapter, that is capacitors and capacitance. Before going to that topic, a small part is remaining in the previous topic, that is effect of polarization of dielectrics on external field. In the last class we have studied the polarization of dielectrics, that is when a polar or non-polar dielectric, when it is placed in the external field, the molecular dipoles aligned along the direction of electric field. As a result of this, net dipole moment is developed in case of or induced in case of dielectric substance, isn't it? Now, due to polarization, is there any effect on the external electric field? That we are going to study in this part. Okay. Now, this diagram represents the dielectric. It may be polar or non-polar in the presence of external field. So when the dielectric is placed in the external field, molecular dipoles gets aligned along the direction of electric field. This will be the situation. Okay, all the dipole moments will be along the same direction, therefore net dipole moment of the substance is not equal to 0. Now imagine it as a dielectric slab. It may be of rectangular shape or square shape, anything, totally it is a dielectric slab. Now, inside this dielectric slab, if you consider a small volume delta V, okay, small volume delta V, if I consider a small volume delta V in this part, just for example, okay, delta V, then in this volume, the positive charge of one molecular dipole sits close to the negative charge of another. As a result of this, if you calculate the net charge of this volume element or volume, then net charge of this volume, I represent it as Q delta V, it is equal to 0. So, if you consider a small volume, inside that volume, positive charge of one molecular dipole sits close to the negative charge of the other. As a result of that, this net charge of that volume, small volume, it is equal to 0. Now, this condition is true anywhere inside the dielectric. We know that dielectric is made up of, this is just a representation. Actually, dielectric consists of very large number of molecules. So, anywhere if you consider a small volume, then net charge of that volume is 0. So that means inside the dielectric substance, net charge is equal to 0. Now, consider the surfaces. Two surfaces of this dielectric slab. Slab will be like this surface and this surface, which are perpendicular to the electric field. Now, electric field is in positive x direction. One plane is here, parallel to YZ plane, another plane is here parallel to YZ plane. Now if you consider these two surfaces, on this side, from the diagram itself it is clear that on this surface there is net accumulation of negative charge. So there is no other positive charge to cancel the effect of this negative charge. So on this surface, that is first surface which is perpendicular to electric field, there is accumulation of negative charge. If you consider the other surface which is perpendicular to electric field, on this side there is net accumulation of negative charge. See here, okay, net accumulation of positive charge. Sorry, it is not negative, it is positive charge. So on this surface of the dielectric, there will be net accumulation of negative charge due to polarization, and on this surface there will be net accumulation of positive charge due to polarization. We know that if there is potential difference, that is plus and minus, if there is potential difference between any 2 points, electric field is produced. Now in this case, in this side we have net positive charges because of accumulation of positive charges. Here we have negative charges. Therefore, due to polarization of dielectrics, an electric field is developed. We know that the direction of electric field is from positive to negative, or from higher potential to lower potential region. So electric field is developed, which is, or I'll represent that electric field as EP, that is electric field produced by polarization of dielectrics. dielectric. Now if you consider the direction of this electric field, it is directed from positive to negative, like this. Now just to compare the directions, external electric field which polarized the dielectric is in positive x direction, whereas the electric field produced due to polarization of dielectric is in negative x direction. That means these two electric fields are opposite to each other. Now consider the region in which we placed the dielectric substance. In that region, if you consider the region in which dielectric substance is placed, net electric field is equal to electric field, that is external electric field. The direction is opposite, therefore electric produced due to polarization. Okay, net electric field in this region is equal to external electric field which is used to polarize the dielectric minus electric field produced due to polarization. Negative sign is because the direction of these two electric fields are opposite to each other. I think it is clear. Now what is the effect of this polarization? That is explained here. That means due to polarization of dielectrics, whenever a dielectric is placed in a region, due to polarization of dielectric, in that region strength of external electric field decreases. Okay, due to polarization, strength of external electric field decreases. So net electric field is given by external field minus electric field produced by polarization. Now this is the effect of polarization of dielectrics on external field. So net electric field is equal to E minus EP. Okay. Next let us consider two more terms here. Now there is a limit for this external field. In case of a given dielectric medium, we can apply an external field to a dielectric medium to a particular extent. Okay, so for a given dielectric medium, there is a limit for electric field. If you apply an electric field which is greater than that limit, straight away ionization of this dielectric takes place. Formation of ions. Okay, ionization of dielectrics takes place. So once dielectric undergoes ionization process, it changes its state from non-conducting to conducting state. Okay, so insulator or non-conducting material is called dielectric. When a dielectric is subjected to very large external electric field, under that condition that material may undergo ionization. Due to that ionization, the effect of ionization is that dielectric material changes its state from non-conducting to conducting. So that limiting value of electric field is called dielectric strength. Dielectric strength of the dielectric material. Now dielectric strength is nothing but it is the maximum electric field, external field, maximum electric field up to which the dielectric stays in non-conducting state. Or in other words, it is the maximum electric field beyond which the dielectric undergoes ionization or retains its non-conducting state. That is called dielectric strength. Now the strength of that electric field at which the dielectric undergoes so that is electric field, the phenomenon in which due to application of very large electric field, dielectric undergoes changes its state from non-conducting state to conducting state. It is called dielectric breakdown. Dielectric breakdown. So due to application of large electric field which is greater than dielectric strength of a medium, then that dielectric medium undergoes ionization or ionization takes place, due to that it changes its state from non-conducting to conducting state. That condition is called dielectric breakdown. That is due to ionization. Due to ionization, when large electric field is applied in case of dielectric, due to ionization, if dielectric medium changes its state from non-conducting state to conducting state, okay, non-conducting to conducting state, then that condition is called a dielectric breakdown. Now in case of air is a dielectric medium. In case of air, the dielectric strength is, okay, dielectric strength of air is 3 into 10 to the power 6 volt per meter. In case of air, if you apply an electric field which is less than 3 into 10 to the power 6 volt per meter, air will be in non-conducting state. If external electric field strength crosses this value, now actually this is dielectric strength of air, okay, maximum electric field. If external field crosses this value 3 into 10 to the power 6 volt per meter, okay, electric field strength crosses that value, then ionization of air takes place, and due to ionization of air changes its state from non-conducting to conducting. Okay, so that is dielectric strength of air. Okay, air. I think it is clear. Maximum electric field up to which the dielectric substance retains non-conducting state, or maximum electric field at which the ionization of dielectric takes place, beyond which ionization of dielectric takes place, is called dielectric strength. And due to ionization, dielectric medium changes its state from non-conducting to conducting state. That condition is called dielectric breakdown. This is the value in case of air, 3 into 10 to the power 6 volt per meter. If field is less than 3 into 10 power 6 volt per meter, then air will be in non-conducting state. That means it will behave like insulator. If electric field is greater than that, ionization of air takes place so that it changes its state from non-conducting to conducting. Okay, I think it is clear. This is about polarization of dielectrics. So next is second part of this chapter, that is capacitors and capacitances. Sorry, capacitors and capacitance. Now, first of all, let us try to understand these two terms, capacitors and capacitance. Now, a capacitor. A capacitor. What is a capacitor? A capacitor is nothing but it is a device. Device which is used to store electric charge or energy. Okay. The device which is used to store the electric charge or energy is called a capacitor. What is capacitance then? Capacitance is nothing but it is ability or capacity to store charge. Capacity of a material to store charge or ability of a material to store charge is called capacitance. Okay, capacitor is a device which is used to store electric charge or electrical energy, and capacitance means it is the ability of that device or any material to store charge, that is called capacitance. Now let us try to understand the term capacitance. Okay. Now let us consider the case of a conductor, spherical conductor. Okay. Spherical conductor. Now in case of this spherical conductor, whenever this spherical conductor is charged, we know the property of charge. We already discussed these things in previous videos. Whenever a conductor is charged, charges always reside at the surface of the conductor. Since the surface is uniform, there will be uniform distribution of charge on this surface, on the surface of this sphere. Now let R be the radius of this spherical surface, R be the radius, and let Q, now positively charged, the charges are positive, so conductor is positively charged. So in case of this positively charged spherical conductor, electric field is directed outward and it is normal to the surface at each point. We have studied all these things in previous videos. Inside the conductor, electric field is 0. We know everything. Okay. Now, on the surface of this conductor, potential is given by, potential due to charge stored in spherical conductor on its surface is given by 1 by 4 pi epsilon naught, magnitude of charge divided by distance from the center to the surface is equal to Q divided by R. Okay, Q divided by R. Now, just rearrange this equation. 4 pi epsilon naught, I will shift this 4 pi epsilon naught to this side. 4 pi epsilon naught R is equal to Q divided by V. Okay, 4 pi epsilon naught R is equal to Q divided by V. Okay, now what is this Q divided by V? Q divided by V is nothing but it is the ratio of amount of charge stored in this particular conductor to potential on it. Isn't it? Potential on it. So Q divided by V. Now if you consider the left hand side of this equation, it is a constant. Q divided by V is a constant. 4 pi epsilon naught, all these things are constant, and R represents radius of the conductor, so 4 pi epsilon naught is constant. That means in case of a conductor, for simplicity I consider the example of a spherical conductor. This is true for all the conductors, conductor of any shape. If you consider the ratio of amount of charge stored in a conductor to the potential on it, you will get a constant value, and this ratio is called, or it is represented as C, and it is called its capacitance. The ratio of amount of charge stored in a conductor or material or device to potential, to its potential is a constant, and that constant term is called capacitance. Okay, capacitance. See, if you increase the value of Q here, V increases. Or in other words, if you increase the potential, amount of charge increases. That is, V is directly proportional to Q. When V is directly proportional to Q, Q divided by V is a constant, and that constant is the capacitance of that particular device. Now in this case, it is the capacitance of the conductor. Okay. Now, what is the unit of, SI unit of capacitance? Capacitance is given by Q divided by V, Q coulomb. Potential, in the denominator we have potential, unit of potential is volt. So SI unit of capacitance is coulomb per volt or coulomb per volt, or we use another unit, that is farad, which is represented by capital F. SI unit of capacitance of a material or a capacitor is expressed in terms of farad. Okay, capital F. Now 1 farad is equal to 1 coulomb per volt. This is the definition of unit of capacitance. Capacitance of a conductor or a capacitor or a material is said to be 1 farad when 1 coulomb of charge stored in it produces a potential of 1 volt. If 1 coulomb produces 1 volt potential on it, then capacitance is said to be 1 volt. That is the definition of capacitance. So SI unit of capacitance is farad. Okay, I think it is clear. Now from this expression, if you consider this particular expression, if you consider the capacitance of this particular conductor, which is true for all the conductors or materials, this capacitance is independent of Q and V. Q and V. Capacitance does not depend on Q, or capacitance does not depend on V independently. It is independent of Q and V, and the capacitance value just depends on 4 pi epsilon naught R. Now what is R? r is the radius, that means it is related to dimension of the conductor. So capacitance depends on the dimensions or geometry. Dimensions means it may be size or shape. Size and shape of the conductor. At the same time, this capacitance, one more term is there, 4 pi epsilon naught into r, 4 pi epsilon naught. Now this constant term is the case when this conductor is surrounded by free space or air. If any other dielectric medium exists in this region, then this equation straight away becomes 4 pi k epsilon naught. That means the capacitance depends on the surrounding medium or the dielectric. Okay. Dielectric medium in which the conductor is placed. And this capacitance is independent of Q and V. That is magnitude of charge or potential. I think it is clear. Capacitor is a device used to store the charge. Capacitance is capacity to store charge or ability to store charge. In case of conductor, potential is given by this expression, where this, if you consider the ratio of charge to potential, we get a constant value. The ratio of amount of charge stored in a material or conductor to potential on it is a constant, and that constant is called capacitance of that particular material. Capacitance is measured in terms of farad. Capacitance of a material is said to be 1 farad if 1 coulomb of charge produces 1 volt of potential on it. Next, capacitance of a material is independent of Q and V. It depends on the dimensions like size, shape, etc. and the dielectric medium in the surrounding region. Okay. This is about capacitance. Now what is capacitance? It is the ratio of charge to the potential. Okay. Let us continue our discussion further. Next, what is a capacitor? Now we discussed the term capacitance. Next, what is a capacitor? As I said already, it is a device. Okay, it is a device. Now, consider a conductor. For example, a plane sheet. In the previous case, I considered a spherical conductor. Now, in this case, consider a plane sheet like this. Conductor of any shape. It may be wire also, no problem. Totally, it is a conductor. Now this conductor is actually neutral conductor. Okay. Now I'll explain. I'm going to explain the principle of capacitor. Okay, principle of capacitor, which is not included in your syllabus. But still, what is capacitor? That is important. That's why I'm going to discuss the concept, the principle of capacitor. Now, if this is a conductor, now this conductor can be charged, or we can store charge in this conductor in different ways that you have studied in previous chapter. Imagine this conductor is positively charged. That means electrons are removed from this conductor. So magnitude of positive charge goes on increasing. That means now this conductor is charging. Okay, charging. For this charging process, there is a limit. There is a limit. That is decided by the potential value. Potential value. Okay. In case of a conductor, there is a limit for potential value. When this potential on the conductor reaches its maximum value, that is the limiting value, up to that point you can charge this conductor, or you can add charges to the conductor. So charging process is possible up to this limit. When this potential on the conductor reaches its maximum value, after that it is not possible to add charge to the conductor. If you try to add further charges to the conductor, those charges will escape into the surrounding medium. Now for example, imagine this as a conductor. if I want to charge it positively, I can remove electrons from this. So when this material is charged, we know that V is directly proportional to Q. As magnitude of charge in it increases, potential also increases. But for this potential, there is a limiting value, that is maximum value. Up to that maximum value, I can charge this material. Once the potential on this conductor reaches its maximum value, after that it is not possible to add charges to this material. Okay, if you try to add, those charges will escape into the surrounding medium. So there is a maximum limit. Now it is charged. Now imagine that potential is now maximum on the conductor. Potential reached its maximum value. After this, charging process of this conductor is not possible. Now what I do is, I'll place an uncharged conductor near this charged conductor. Uncharged conductor near the charged conductor. That means it contains equal number of positive and negative charges. When an uncharged conductor is placed near a charged conductor, we know that charging by induction takes place. Without contact, charging is possible, and that phenomenon or that method of charging is called charging by induction. Now in this case, charging by induction is possible. Okay, charging by induction is possible. So due to that charging by induction, so this material consists of equal number of positive and negative charges. This conductor is positively charged. So negative charges in case of this conductor will be attracted towards this side. So for example, this is positively charged. Positively charged. Now all the negative charges will be attracted towards this positively charged conductor. So there will be net accumulation of negative charges on this surface of this conductor. At the same time, this positive charges will repel the positive charges present in this uncharged conductor. So there will be accumulation of positive charge on the other side of the second conductor. Now what is the effect of this? What is the effect of this presence of this second conductor here? See, we already charged the first conductor up to its maximum possible value. That means potential on the surface of this conductor reached its maximum possible value. After that, charging process is not possible. So what we have done is we placed another conductor here. In case of that conductor, due to charging by induction, there is net accumulation of negative charge on this side and positive charge on this side. Now, due to presence of this negative charges, we know that at any point net potential is the algebraic sum of potential due to individual conditions. Potential due to this conductor is positive here. Due to presence of this negative charges on this part of the conductor produces a potential here which will be negative. Now what is the net potential? What is the net potential on this conductor? Positive due to this one, negative due to this one. If I represent new potential, that is in the presence of this conductor, if V dash is the potential on the conductor here, then surely V dash will be less than V, because this conductor produces negative potential, isn't it? Along with that, these charges will produce positive potential here, but if you consider the distance from negative charge to this conductor and positive charge to this conductor, this distance is less. Therefore, negative potential due to this conductor will be more compared to positive potential. Okay, totally, by placing an uncharged conductor near the charged conductor, we reduced the potential on the surface of this conductor from its maximum value. Further, due to this, a positive potential is produced near this conductor. How to reduce that potential to zero? Very simple method. I'll just connect this conductor to ground. Okay. We know that Earth accepts all the charges. So when this side of the conductor is connected to earth, all the positive charges will flow to earth, so that on this side net charge will be 0. What about negative charges? These negative charges will not flow to the earth because these are held here by the attractive force of these positive charges. So this attractive force between these two will not allow the negative charges to flow to ground. Okay, so negative charges will be there, positive charges will be reduced to 0 by connecting the second conductor to ground. Now consider the surface of first conductor. Potential due to this one is positive, potential due to these charges is negative. Net potential, if it is V dash, then V dash is less than V. That means we reduced the maximum potential or potential value from its limiting value to some other lower value, that is V dash. What is the advantage of this? Since potential is reduced below the maximum limiting value, we can further add charge to this conductor. Additional charges is possible. So up to a limit, once again, when the potential of this conductor reaches its maximum value, up to that particular limit, we can further add the charges. That means we can add more number of charges to this conductor. That means its capacity is increased. Now this is the principle of capacitor. A capacitor is nothing but it is two identical conductors separated by a small distance. In between these two there is a dielectric medium. Now in this case air is the dielectric medium, and the second conductor is earth connected, or it is a grounded conductor. Okay, what is the advantage of having this condition? In the absence of second conductor, we can add limited number of charges, that is up to a maximum potential on the conductor. After that it is not possible to add the charge. If I place another conductor which is grounded, it is actually neutral conductor. Negative charges will be attracted to this side and positive charges will flow to ground. Due to negative charge, a negative potential is developed near the first conductor, which results in decrease in its potential. When potential decreases, we can add more charges till the potential again goes to its maximum value. That means its capacity of this conductor increases due to presence of second conductor. Now this is the principle of capacitor, which is not in your syllabus. Okay. It is not included in your syllabus, but remember all these points. Presence of second conductor increases the capacitance. Now what is a capacitor? It is a device consisting of two conductors, out of which one is grounded. One conductor is grounded, okay, earth connected, grounded conductor, and it is a device which is used to store electric charge. Okay, it is a device which is used to store electric charge or electrical energy. In case of capacitor, two conductors must be there. Two conductors, different possibilities are there. If you use two conductors like this, that is plain sheets conducting plates, then this is called parallel plate capacitor. Possible parallel plate capacitor. If you use two spherical conductors like this, now out of which one is grounded, if you use two spherical conductors with the one conductor is grounded, then it is spherical capacitor. Okay, spherical capacitor. On one there will be accumulation of or positive charges is stored, due to induction, negative charge will be stored in the other conductor, and positive charge of this conductor will flow to ground due to ground connection. Here also, if this plate contains positive charge, this plate will have negative charge. Similarly, cylindrical is also possible. A conducting cylinder, outer cylinder, which is positively charged, positively charged outer cylinder, inside which another cylinder, conducting cylinder is placed, which is grounded. This will have negative charges. Negative charges. So now this is cylindrical capacitor. Cylindrical capacitor. Now in this chapter or in our syllabus, there is only discussion of parallel plate capacitor. Cylindrical and spherical capacitor is not included in our syllabus. Now, in case of capacitor, two conductors will be there. It may be two spheres, or it may be two cylinders, or it may be two plates. In one plate or in one conductor, positive charge is stored, and if plus q is the magnitude of charge stored in one conductor, then in second conductor, that is earth connected or grounded conductor, in case of grounded conductor, there will be negative charge. What about the magnitude of charge? So in case of capacitor, when you place two conductors together, one charged and another one uncharged, charging by induction takes place. Charging by induction takes place. Therefore, if you consider the magnitude, amount of charge stored in the second conductor, magnitude wise it will be same, but polarity is different, so minus q. In parallel plates, if one plate consists of plus q amount of charge, for example plus 2 coulomb, then second plate will have minus 2 coulomb charge. In case of spherical conductor, if outer conductor carries a charge of some 10 coulomb, then inner conductor will carry a charge of minus 10 coulomb. Cylindrical, again same values, positive, one is positive and another one is negative. So amount of charge stored in one conductor is equal to amount of charge stored in other, but polarity is opposite because charging by induction is taking place in case of capacitors. Now let us derive an expression for capacitance of a parallel plate capacitor. Important from the board examination point of view. Derive an expression for capacitance of a parallel plate capacitor. Capacitance of a parallel plate capacitor. Expression for capacitance of a parallel plate capacitor. Now, imagine a parallel plate capacitor like this. One of the plate of capacitor. First plate, let it be first plate, like this. Like this. Let it be positively charged, plus q plus positively charged, and let plus q be the amount of charge stored in that capacitor. We know that a capacitor consists of two conductors. If one is the plate, there will be another plate, parallel plate it is. Another metal sheet will be here, metal sheet. Now actually this is grounded conductor, but no need to show that ground connection. It is understood that second plate is grounded. That means this will have negative charge. Now identical plates of equal area and equal dimensions, negative. Then amount of charge stored will be minus q. Minus q. plate 1 and plate 2. In diagram, the separation between the plates is very large, but actually separation between the plates of capacitor will be very small, so that size of the capacitor will be smaller than this chalk piece. That means it is very close packed structure. Now in between these two conductors there will be a dielectric medium. It may be paper, it may be mica sheet, it may be plastic, or it may be ceramic, anything. Total it is dielectric. In this case, let us consider air capacitor, that is two conductors are separated by air, or in between the region of two conductors let the dielectric medium be air, that is air filled capacitor. Okay, now let us consider three regions: region 1, region 2 and region 3. First region outside the capacitor near the positively charged plate, second region outside the capacitor near the negatively charged plate, and third region is between the plates of capacitor, that is three regions. Now let A be the area of each plate, area of plates, parallel plates, each plate, identical plates, therefore area. Q is the amount of charge stored in each conductor. Okay, Q is the amount of charge stored. Then sigma is equal to Q divided by A, charge by area of cross section. Sigma represents charge density. Q is the area of each plate of the capacitor. Q is the amount of charge stored. Sigma, it is called charge density. Q divided by A. Now in case of this, plus Q plus sigma is the charge density. In case of this plate, minus sigma is the charge density, because minus Q is the amount of charge stored. I think it is clear. Now in first chapter, using Gauss law, we derived an expression for electric field at a point due to charged infinite plane sheet. Now due to we considered a parallelepiped and different things, and we derived an expression for electric field at a point due to charged infinite plane sheet. That expression is electric field E is equal to sigma divided by 2 times epsilon naught. Right. This expression we derived in previous chapter, that is using Gauss law. Second application of Gauss law, electric field is given by sigma divided by 2 epsilon naught in case of a charged plane sheet. Okay, now let us try to write the expression for electric field due to this capacitor or this arrangement in these three regions. Expression for electric field here, here and here. Now first of all, consider the region 1. First region. Two sheets are there. One is positively charged and another one is negatively charged. Now due to this sheet, electric field will be in this direction. We know that due to positive charge, or electric field is directed from positive to negative or positive to infinity. So in this region, if you consider the electric field, this is the direction of electric field due to first plate, whereas this is negatively charged. So electric field due to negative plate will be like this, E2. The meaning is very simple. If you place a unit positive charge here, positive charges will repel unit positive charge, negative charges will attract unit positive charge. Therefore, force on unit positive charge is upwards due to positively charged plate, and force on unit positive charge due to negative plate is downwards. Sigma is the charge density. So electric field due to first plate can be written as sigma divided by 2 epsilon naught. Electric charge density in the second place is minus sigma, therefore electric field can be written as minus sigma divided by 2 epsilon naught. In region 1, net electric field. Net electric field is equal to E1 in upward direction minus E2, or simply straight away I will write the expression due to first plate sigma divided by 2 epsilon naught, due to second plate minus sigma divided by 2 epsilon naught is equal to 0. Okay. So one electric field is in upward direction and another one is in downward direction. So E1 minus E2 net electric field is equal to 0. Let us consider the region 2. Outside the capacitor, at a point outside the capacitor near the negatively charged plate. Now if I place a unit positive charge here, this negatively charged plate will attract the positive charge in this direction. So E2 will be the E2 electric field, it is directed towards the negatively charged plate, whereas this plate will repel the unit positive charge. Therefore this is the direction of electric field due to first plate, E1 and E2 once again opposite to each other. So net electric field in region 2 is equal to sigma divided by 2 epsilon naught, that is first plate. E2 is in opposite direction, therefore minus sigma divided by 2 epsilon naught, it is also equal to 0. Electric field at this point 0, electric field at this region is 0. Next consider the region 3. Region 3 between the plates of capacitor. Now if I place a unit positive charge here, negatively charged plate will attract unit positive charge. Now this is the direction of electric field due to second plate. Positively charged plate will repel the unit positive charge. This is the direction of electric field due to first plate. E1 is directed downwards, E2 is also directed downwards. Therefore in region 3 net electric field E is equal to, due to first plate sigma divided by 2 epsilon naught, we applied this formula, sigma divided by 2 epsilon naught. E1 and E2 are along the same direction, therefore E is sigma divided by 2 epsilon naught plus sigma divided by 2 epsilon naught. Here direction is opposite, therefore minus, direction is opposite, therefore minus. Here direction is same, therefore sigma divided by 2 epsilon naught by sigma divided by 2 epsilon naught is equal to sigma divided by epsilon naught. Okay, sigma by epsilon naught. Now this can be written as E is equal to sigma is Q divided by A, substitute that here, sigma is Q divided by A, therefore E is equal to sig Q divided by epsilon naught into A. Now this represents expression for electric field between the plates of capacitor. Sigma is equal to, E is equal to Q divided by epsilon naught into A. Now next, now let us calculate, see this plate carries positive charge, this plate carries negative charge, that means there will be a potential difference between those two plates. Now let us calculate the potential difference between those two plates. Potential difference, or simply potential between the plates of capacitor. What is the definition of potential? In general, potential is defined as it is the amount of work done in bringing a unit positive charge from infinity to a point. That is in case of a point charge. Now in case of a capacitor, potential or potential difference between the plates of capacitor is nothing but it is the amount of work done in shifting. So potential between the plates of capacitor. Potential between the plates of capacitor is nothing but it is the amount of work done, okay, work done in moving or shifting a unit positive charge from negatively charged plate to positively charged plate. To positively charged plate. or conductor. This is the definition of potential in case of capacitor, or potential difference between the plates of capacitor. Amount of work done in moving unit positive charge from negatively charged plate to positively charged plate is called potential or potential difference. Now it is clear that this definition, from this definition it is clear that charge is shifted from negative plate to positive plate. Direction of electric field is from positive to negative. Against that, work is done in shifting unit positive charge from one point to another. So against the electric field, that is understood. Okay, so potential. Therefore, potential difference between the plates of capacitor can be written as, it is nothing but it is the work done in shifting unit positive charge. Work done in shifting unit positive charge means work done against the net electric field. We know that work done is equal to force into displacement. Use same concept. Now in this case, force acting on the unit positive charge is electric field. So force is E. Okay, E, and let the separation between the plates of capacitor be D. Distance between the plates of capacitor be D, then work done can be written as force into displacement. Force on unit positive charge is electric field into displacement is D. So that means V is equal to, now what is D? Q divided by epsilon naught A. So Q divided by epsilon naught A into D, electric field into D. So Q D divided by epsilon naught A. Okay, epsilon naught A. Now we know that capacitance of a system or device is nothing but it is the ratio of magnitude of charge to potential, Q divided by V. Okay. Now the capacitance C is equal to, definition of capacitance is, it is the ratio of amount of charge stored to the potential, that is Q divided by V by definition of capacitance, is equal to, now in this case Q is the amount of charge stored, divided by V is Q into D divided by epsilon naught into A. Q into D divided by epsilon naught into A. Now this Q cancels with this, epsilon naught A comes here. So capacitance C is equal to epsilon naught A divided by D. Okay, capacitance is equal to epsilon naught A divided by D. This is the expression for capacitance of a parallel plate capacitor. We started with this structure. Two conductors, two parallel plates, one is positively charged and another one is grounded, therefore it will carry same amount of charge but a negative charge, minus Q. We consider the three different regions. In region 1, electric field due to positive plate is upwards, negative plate is downwards, net field is in this region is 0. Same condition satisfies here, net field in this region is also equal to 0. Okay. Next, if you consider the region between the plates of capacitor, electric field due to positive plate is towards the negative plate, electric field due to negative plate is also towards the negative plate. Therefore, in the region 3, net field is, now here we used the expression that we derived in using Gauss law in case of infinite plane sheet. Sigma divided by epsilon naught is the electric field, therefore net field is equal to, due to positive plate plus negative plate, it is equal to sigma by epsilon naught. Sigma is the charge density, therefore we replaced sigma by Q divided by A, charge by area. So we got the expression for electric field, Q divided by epsilon naught into A. Next, that expression is substituted here. Now potential or potential difference between the plates of capacitor is nothing but it is the amount of work done in shifting a unit positive charge from negatively charged conductor to the positively charged conductor against the electric field. Therefore that work done can be written as force into displacement. Force is the electric field, displacement is the separation between the plates of capacitor, that is equal to D. So after substituting electric field we got this expression. Next, the definition of capacitance, that is C is equal to ratio of charge to the potential. So potential is this one, substituting the potential value, final expression for capacitance is C is equal to epsilon naught A divided by D. That is the final expression. capacitance of a parallel plate capacitor. Okay, we'll continue the discussion on this topic in the next class. Okay, thank you so much.